Hey, Chem fans, you'll have to bear with me today. I'm feeling a little blue, a little basic, but I'll get over it, right? I can explain the difference between strong and weak acids and bases. That is our target today. If anything's going to get me out of feeling blue, it's Benny Boy. Look at him working hard on his work. Oh, what a boy. Anyway, one of our targets today is to figure out what happens when you have things such as an acid or a base, and you mix those two things together. So you should be able to tell me what will happen when an acid and a base will mix together, like sodium hydroxide and hydrochloric. You should be able to figure out which one's which. Then you can see that I've got a whole bunch of acid-base reactions, and I want you to figure out who's the acid, who's the base, who's the conjugate, acid and base, which should be pretty easy if you think about proton football, right? So pause me, try out the questions, write them down in your ETD, and see what you know, and we'll tackle them together. So if we look at this first one, what happens if an acid and base are mixed, such as sodium hydroxide and hydrochloric? Well, if we look at the hydrochloric, that starts with a hydrogen, so you know that that thing is, of course, your acid. That is the thing that's going to, of course, dissociate. And as an acid, as we know from the definition, it's a proton donor. Thank you, Bronsted and Lowry, right? I want to combine that together with sodium hydroxide. And of course, when I do this, I want them to do their job, so I got to put them in the water. They're both aqueous solutions. When I do that, one thing I'll notice is Bronsted and Lowry said that a sodium hydroxide or a base is something that produces and causes hydroxide ions to be in solution. It is a proton acceptor, as Bronsted and Lowry. Arrhenius said it was a hydroxide producer, right? This, of course, is my base. So what I'm doing is I'm putting these two things together. You can see they have their other components. And when they do that, they're two solutions. They can do the old switcheroo. What's going to come out the other end? Always. Well, one part of it that you can always make, as you can notice, this is an H plus an OH. Hey, that makes HOH. It makes H2O. That's one of the crucial things that we should notice. Acids and bases are actually the opposite sides of water. But that's not all I make. If I just do the old switcheroo, I can see that I also make this stuff called sodium chloride. Hey, that's a salt. And I will always produce this thing called water because I'm having an acid and a base tempered together, and it's a brand new water. So acid and base reactions always produce two things. They produce a salt and water. Now, the importance of this is recognizing that's why they're always in solution, because they are the opposite sides of water, and water being there helps to have these reactions happen. Now, let's imagine that you did this for a long time. Let's say that you had a bunch of rocks on Earth that were made of things like sodas, which are basic materials, and calcium carbonate, limestone, stuff like that. And you had the atmosphere rain down water, which is slightly acidic in most situations. Or you had a bunch of plants and animals pee all over it for, say, millions and millions of years. You'd have a lot of acids mixing with bases, the rocks mixing, of course, with the effluent from the animals, the excretions of the acidic stuff, and the atmosphere. You'd make a lot of salt and water. And that would explain why the oceans are salty, because, that's basically what's happened all these years, no pun intended. You've had a bunch of acid-base reactions that continue, so the oceans could get saltier and saltier as time went by. And then, of course, it heats up and evaporates in shallow areas, and you can still collect it today to have all the salt. But that's where all of our salt mines come from, like Salt Lake City and all that stuff. That salt is from former oceans that have evaporated away and got saltier, or lakes that have been trapped for a long time and gotten saltier. Hey, not this has anything to do with real life. It's just why, your tears are salty, because you evolved from an ocean-going fish that lived in a salty ocean. Thanks for all that pee and acid-base reactions, right? The other part has to do with conjugates. So let's get some notes first. If we look at conjugates, and you know your Spanish, you know it says con, which means with. If we look at these conjugates, they're the transfer of a single proton between an acid and a base. A single proton, and that's crucial. It's just one proton. Don't get too excited about proton football and start chucking extra balls, right? This is a single proton between an acid and base, which makes it relatively easy. And don't forget, a proton is a hydrogen ion. So if I look at my reactions that I have here, my job was to identify the acids, bases, and the conjugates, right? Well, anytime you're looking for an acid, it's easy. You look for the hydrogen out front. Hey, there's one. This is my acid. What would you call it? Well, back to naming. Hey, that's a nitrite ion, ick, got a I to us, so this is nitrous acid, and I'm mixing it with an OH. Hey, that's a hydroxide. That's got to be my base. That's my receiver, right? What's going to happen here, of course, is my acid is going to throw the proton and become Well, this thing, a nitrite ion, that's my conjugate base. It's the new receiver, right? Cool. And if I look at my base, that's my receiver, it's going to become H2O, which in this case, water is acting as my conjugate acid. That's why the H is going out in front of that thing. So, of course, the nice thing is the pairs will always logically make sense. That's a change of one proton. And if you see a hydrogen out front, it's a pretty good indication that's the acid part of this, right? If we look down at the next one, we can see this chemical right here. Hey, it starts with an H. Must be a proton quarterback, right? That's my acid. And this one would be called perchloric acid, right? It's one of those naming rules. I'm mixing it together with the other substance, in this case, water. So water is going to act like my base because it can do that. It's awesome, right? When I put those together, my acid throws the ball, and when it throws the ball, it loses the proton and becomes the ClO4 thing. So now it was the quarterback, now it's the conjugate base, the new receiver. It becomes a perchlorate ion. And the water was acting as my base because it's my receiver. When it receives it, it becomes the conjugate acid. Because now it's got the ball, it's ready to throw it back here. And it can go back and forth through those things. This H3O plus is called a hydronium ion. It's a fancy name for hydrogen ions in water because that's what they really do. They get grabbed on by other waters. So that's a good one to keep track of. It's pretty important. Keeps you alive every day, right? If we look at the last one, hey, this chemical doesn't have an H. Well, it must be acting as my base, which means that water in this case is acting as an acid because it can do whatever it's needed to do. It depends on what it's surrounded by, right? That means, of course, that my acid is going to throw the proton and become my conjugate base. And now, of course, it's a hydroxide ion. Hey, that's what a base is. And if we look at this, we can also see that the fluorine ion becomes HF. Hey, that's got an H out front, so this is now my conjugate acid. It was my receiver. Now it's my new quarterback. And it can throw that stuff. Now it's this stuff called hydrofluoric acid. Pretty nasty stuff. Can eat away. It's not only your teeth, but your bones in a gaseous form, right? So the nice thing about the pairings of these is they're easy to predict. If you only exchange one proton, you can figure out their actual chemical formula and what the conjugates would be. Now the question is, of course, who's the better quarterback? And that's what we'll get into today. So if we look at this, you got your notes out, and we're going to dig into this idea of making sure we can identify the conjugates really fast. So you should write down these examples. For the first column, I want you to write the conjugate base for each of those. And for the second column, I want you to write the conjugate acid for each. Pause me, see if you can do it on your own, and then we'll see if you got this down. I don't get a break. So, cool. Bring it back. If we look at this, this is H2S. So if I'm going to double check that, well, it's proton football. To make the base, this has to be the acid. So when it throws that proton, it becomes HS1 minus. It went from this thing called hydrosulfuric acid to now it's this hydrogen sulfide ion, right? Okay. Hey, it's more proton football. That's still got another proton. It could throw that one, and then this hydrogen sulfide ion could become a sulfur 2 minus ion. It's just losing one proton, so that means that its charge goes into negative ion one more step, right? This is a hydronium ion. It's acting as an acid, so I need the conjugate base. If it throws a proton, it becomes water, because water can become a base as well, right? Then I got this HClO stuff. Well, if it's the acid, make the base, I just chop off the hydrogen ion. Now it's a ClO1 minus. It goes from being a hypochlorous acid to this thing called a hypochlorite ion. If I go over here, I can see that I want the conjugate acid, which means all of these are acting as bases, and bases are proton acceptors. Thank you, Bronsted and Lowry. If we look at this NO3 1-, a nitrate ion, would become HNO3. Hey, that one positive just neutralized that 1-, and now it's this, well, it's HNO3. That's, got I to us. Woo! This is a nitrate, so it becomes a nitric acid. That's the trick to it, right? Don't forget the songs. ClO1 or Cl1- would gain a proton and become HCl. So it goes from being a chlorine ion to hydrochloric acid. Notice that I need the hydro because there's no oxygen attached. Naming is never going away. SO4 2- is a sulfate ion. So that will add a proton onto it and become an HSO4 1- because I can only add one proton. This is now a hydrogen sulfate ion, right? PO4 3- throw a proton on it, it grabs onto it, it becomes HPO4 2-. It's now a monohydrogen phosphate ion, which there's always more naming rules to learn. So hopefully you notice, of course, figuring out conjugates is fairly easy if you just remember you're exchanging one proton. The quarterback throws the proton, the base receives it. All right. Now, other things that we need to know that are pretty crucial, right? I want you to write down this question. I want you to draw and explain what this figure that I'm about to put up says about the difference between strong and weak acids, and would they have a small or a large KEQ? So here's the graphic. Write down the question, sketch out the graphic because it's a really good one. You can see that there are these wonderful bar graphs as well as the microscopic pictures on the right-hand side. Cool. Now, if we take this on together, we can see that basically what we've got going on is this is HA. It's saying it's a strong acid. And you can see that after dissociation, well, like all of it became H plus A-. It dissociated completely. And that's why inside the beaker, they're not connected together. They are completely dissociated. Those are quarterbacks that love to throw protons. That's burn your face off strong, right? If we look at the weak acid after dissociation at equilibrium, because it can make and break back and forth, you can see that in my bar graph, I still got lots of the original quarterback. He didn't throw the ball much. He's shy about throwing it. And he only threw a couple of those protons, so only a few of them are dissociated. So the difference between a strong acid and a weak acid is how much they dissociate, but that's why we stress dissociation so much this year. It decides whether or not they will burn your face off. So this is another version of that. Unfortunately, in India, there are some parts of the country where if you want a divorce from your husband, they will sometimes throw strong acids like hydrochloric on your face. And that's what happened to this poor lady. That hydrochloric, of course, is a strong acid because it dissociates completely. So those protons then attack you. So as we go into labs, you would want to make sure you were really careful with strong acids and could identify them. We've already started talking about them this year. It's because they dissociate completely, which means they can burn your skin very, very well because there's lots of protons into play, right? Now, this you want to write down, strong acids are strong donors, which is another way of saying they are good proton quarterbacks, right? So things to add into this. Strong acids that we need to worry about for this class, hydrochloric, sulfuric, and nitric acid, right? For our means in terms of our class, the rest will just be considered weak. There are other strong acids, not that you're going to face in regular inorganic chemistry. So let's take a look at how this works. If we look at HCl, HCl, of course, to be an acid, it has to be aqueous. I got to put it in the water. This would be my strong acid, right? So let's switch colors here a little bit. And that strong acid, of course, is a good quarterback. So what's he going to do? He's going to be making and breaking, but he's going to dissociate and become hydrogen ions, protons, and chlorine 1- aqueous ions, right? What this means is this is going to completely favor going in the forward direction because this thing likes to throw the ball. It's like a Tom Brady, right? This dissociates completely. And when it dissociates completely, it puts lots of protons into solution. That's what makes it strong. And then it becomes this chlorine 1-. Now, the key of this is if they are a strong quarterback, it's because they like to throw the ball. They don't like to catch it back, which means it becomes a weak conjugate base. So anybody that's a good quarterback is a lousy receiver, essentially. And what that means, of course, is if we look at the KEQ for this one would be heavy in the product, the forward reaction, and low in the reactants, the acid that started off, so it has a really high KEQ. It favors dissociating. Hey, we can use equilibrium stuff because it can make it break back and forth, but it definitely favors the forward reaction. It's a really bad arrow, right? Then, of course, there are things called weak acids. And a good example of a weak acid is one that you eat on, say, chips. And that's, of course, vinegar. If we look at vinegar, HC2H3O2, it's considered a weak acid. That's why we can eat it at the concentrations that we use it. It can make and break itself because these are all reversible reactions. And it's a quarterback. It's an acid. It throws out protons that are then going to be aqueous. It also produces acetate ions because it's dissociating. They don't just disappear, right? When they do this, of course, though, it's a weak acid, which means they don't dissociate completely. This is a quarterback that likes to hold on to the ball. So what it becomes, of course, is the reason why it holds on to the ball is it's a strong conjugate base. So if it is a weak acid, it becomes a strong base. If it's a lousy quarterback, then it becomes, of course, a good receiver. And that's like the acetic acid throws the ball and then grabs back onto it and becomes, of course, the quarterback again. And that's essentially what's happening here, because this is such a good receiver of the ball. It grabs it back. So when we have weak acids, they, of course, have a KEQ that's going to have very little product and lots of reactant, because they throw the ball and grab back onto it, which means that they're not likely to burn you as much unless you increase their concentration, right? The concentration has an effect here too. This would be a reaction that favors the reverse reaction, because if I'm a strong acid, I become a weak conjugate base. I don't like to catch the ball back. If I'm a weak thrower, a weak acid, then I become a strong conjugate base, and I receive it back and grab onto it as soon as I throw it out there. And that's the difference. And that's why conjugates are so important. These are all reversible reactions, and the strength of your conjugate decides how strong the acid is. If I got a weak acid, I got a strong receiver right at the other end of that. Now, cool things about this, the pattern of that follows the same, strong paired with weak. If I'm a strong base, then I'm a strong receiver, and I become a weak conjugate acid. If I'm a weak base, then I'm a weak receiver, and that's because, of course, I become a strong conjugate acid. So it's always paired up, strong with weak. Great pattern that you can always predict. What's going on here? Well, I got this stuff called water, and I'm mixing it as I take a drink. Mix it with this stuff called HNO3, which is nitric acid. So if we look at this, nitric acid is a strong acid, which means that when it reacts, it's going to dissociate completely and favor the forward reaction to make lots, of course, of hydrogen ions in solution, which become the hydroniums, gobbled up by the water. So water is acting as my base. Well, this stuff called nitric is the acid. It's a strong quarterback, so it favors the forward like crazy. And, of course, that's because the nitrate ion is a weak conjugate base, right? It's a poor receiver. In the other situation, now I'm taking water and I'm mixing it with ammonia. And ammonia is a strong base. Being a strong base, it's a strong receiver. It's going to rip off those protons and become, of course, its conjugate acid, the ammonium ion. This one is not as strong, so it doesn't favor it as much, but it still puts a lot of those into solution. Now, one thing that I can see with this is there's a weird thing going on here. My ammonia, when I mixed it with that, water was acting as an acid. And in this situation up here, I mixed it with an acid. It acted as a base because, of course, the cool thing about water is it can be both. And that's what you should notice about water. You should write down these reactions. Ammonia mixed with water, the water will act as an acid, a proton donor. Water mixed with an acid, water will act as a base. So is it an acid or a base? Well, it's both, right? And the way we say that in nerdy science is we say amphoteric. Should make you think of amphibian, because amphi means both, right? Like an amphitheater. Now, cool things about this, amphoteric is what we define those substances. So I'll write this down. It's a substance that behaves as an acid or a base. And the most famous of all amphoteric substances is water. Cool thing about it is if I mix water with water, well, the water will start to play proton football in a reversible reaction. And the neat thing about that, of course, is that means that some of them will throw and act as the acid, and some will act as the base, and they will make hydroniums and hydroxide ions. Now, they only do it a little bit. They do it like 1 times 10 to the negative 7. And if you put together their concentrations, it'd be like 1 times 10 to the negative 14. But that kind of sounds like 7s and 14s. That sounds like a pH scale, right? Must have something to do with water and proton football. Now, cool things about this is normally today we'd be going after what's called the acid rain lab, or what I would call the acidic environment lab. Just imagine if there was like acid falling from the sky. It'd be terrifying. Well, there is, right? Now, what makes acid rain? It really comes down to what we put into the atmosphere. And there's a couple things that do that. There's air pollutants from things like combustion, like CO2, as well as SO2, sulfate ion or sulfur dioxide, that would come out of things like coal plants. And then, of course, there's nitrous oxide, like things that come out of motor cars and motorbikes and stuff like that, and with inefficient combustion systems. So we're going to simulate that and take each of those and dissolve them into water, just like it does in the atmosphere, because unfortunately there's huge clouds of water and invisible water vapor in the sky, and that mixes with the gases that we put out as exhaust. In our lab today, we'll notice that you'll be blowing bubbles, or would be blowing bubbles, into water. And that's because you produce CO2 that combines with water and makes this thing called carbonic acid. And then another one that you can do is you can take Things like nitrous oxide that would come out of a car exhaust, mix that with water, and that will make things like nitric and nitrous acid, both of those. And one of the things that we're going to be doing is we'd normally be taking a look at the lab and measuring the amount of pH. Remember that below 7 is acidic, above 7 is 14, so we can see how the pH changes over time. And the crucial thing with this is that you take a dropper, and the neat reaction and the second reaction part of this thing is we take some hydrochloric and we're going to mix it with this stuff that's in the bottom of it called sodium bicarbonate. And when we do that, of course, it creates a gas, and the gas that it produces for us, because we do this one actually with hydrogen bisulfite, that would produce a gas that's sulfur dioxide. The cool thing is then we suck up that sulfur dioxide and we bubble that into water and measure how much the pH changes with those things. In the third part of the experiment, it's the most detailed part. You take some hydrochloric, you put it into distilled water, and you measure the pH, which should be acidic. Then you put in, of course, this stuff called calcium carbonate, a base, and you should notice the pH changes. And then the next thing you do after you've swirled it up together and the pH stabilizes is you would take and you'd squirt 2 to 3 more squirts of hydrochloric into the solution that you put both acid and base into, but now you're adding more acid, and you'd watch to see what happens with the pH. And it wouldn't do necessarily what most people expect. It's a buffer, right? Which we'll get into more detail next time. We can't do the acid rain lab this year, but we will do it in the future, and hopefully get the idea that there's these things called conjugates, right? If I am an acid and I'm a strong acid, it means I dissociate completely. I like to throw the ball, and that means that I become, from a strong quarterback, I become a weak conjugate base. And that means I don't want to pick the ball back up. That's something like hydrochloric or nitric acid, right? If I'm a weak acid, like vinegar or carbonic acid, then I don't like to throw the ball. And when I do throw the ball, I go from being a weak acid, I become a strong conjugate base. And that means that I grab back onto the ball, which keeps it from dissociating. So it's all about the rate of dissociation, and the pattern follows the same for bases. A strong base would become a weak conjugate acid, and a weak base, a weak receiver, would become a really good thrower of the ball. So if I'm good at throwing, I'm bad at catching, right? And then you got this thing called water. And the beauty of water is, water, of course, well, it can throw and it can catch. It can do both. Hey, no wonder it's the ultimate buffer. It's kind of a medium quarterback and a medium receiver. Excellent. Buffer that.